Hello, my name is Drew Griffiths, and this is my presentation on the motion of a falling object for Lab 2 of Physics 2211. The purpose of this lab is to observe the motion of an object that falls somewhat slowly and compare its data to two computational models. One of these models only includes the effect of gravity, and one of them includes both gravity and drag. And spoiler alert, the model that included gravity and drag was more accurate than the one that just included gravity, because drag is a prevalent force when objects are falling in the real world. So here are the fundamental physical principles that I use in this lab. I use Newton's second law, which states that F net is equal to the change of momentum over the change in time, which is equal to the mass times the change in velocity over the change in time, and that is also equal to ma. And then F net is also equal to the sum of the two forces, gravity and drag, and the gravitational force is equal to negative mg times y hat, and g is negative 9.8 meters per second squared. And I also use the velocity and position update formulas used in my computational models so that I could update the position and velocity of my crumpled paper ball at various time steps. And then here's the equation for the drag force. So here's a screenshot of my tracker software, and you can see the experiment that I used for this video. I included a yardstick to try and get a more accurate representation of the position of the ball at each time step. Obviously, it's not going to be completely accurate, but yeah. So my initial velocity was 0 because I just dropped it, no initial velocity. And then the initial position was 0.002. Here's the code for the computational model that only included gravity. You can see here the initial position, the initial velocity, delta t, which is the frame rate of the video. G is equal to the gravitational constant. B is equal to the 0 because that is the proportionality constant for the drag force, and I'm not analyzing drag in this model. And then F net is equal to negative mass times g times j hat. That's pretty much just the gravitational force, and then I calculate it using the its velocity and position using the velocity and position update formulas. Then here is my computational model for drag. The only things I changed was I added the proportionality constant, and then I changed the formula for F net. And here I just kept the same gravity force, and then I subtracted the drag force from it to calculate F net. And here are my results. As predicted, the gravity-only computational model fell further than the gravity and drag model in the experiment because it does not have any drag acting on it. And if there were a free body diagram, the force of drag would be pointing straight up and the force of gravity would be pointing straight down. So the force of drag would make the net force in the negative direction a less magnitude, which would slow down the velocity that the object was falling at. And there are some minor discrepancies between the data by the experiment and the drag and gravity, and I will cover those errors in the next slide. So some possible errors in my experiment, like I discussed in the last slide. The discrepancies in the graph were likely caused by inaccurate tracking on tracker, which was my human error, not being able to place the center of mass right in the center of mass was likely off by a little bit. Also, my phone was at a slight angle when I recorded the video, which would make the measurements not quite perfectly accurate. And also, the paper ball wasn't perfectly symmetrical when I crumpled it up and then dropped it. So that means that drag would act inconsistently on each different part of the ball because the center of mass is not perfectly in the center of the ball. So some further questions. Does either model predict a terminal velocity? Neither model reaches a terminal velocity because they don't fall for long enough, but the gravity and drag model shows that it eventually will reach a terminal velocity because the slope in the velocity versus time graph shown here is approaching 0, and if it fell for long enough, it would approach 0, meaning that the acceleration would be 0 and the velocity would be a constant, and it would be at a terminal velocity. And then if the object was thrown downwards instead of dropped, then the terminal velocity would still be the same. Then that object would just reach terminal velocity quicker because it has an initial velocity that's not 0. And that's all. Thank you for watching.